Imagine an AI that teaches itself to think, not by studying our examples but by creating its own challenges, solving them, and learning from the entire experience. This isn't science fiction, it's happening right now, and it's called the absolute zero training method. I'm going to take you on a journey to understand this breakthrough that's not just changing how AI works, but challenging our fundamental ideas about knowledge, learning, and perhaps even consciousness itself. Whether you're new to AI concepts or just curious about where this technology is heading, this video will help guide you through this fascinating territory, explaining complex ideas without getting lost in technical jargon, and even teach you a few key words in the discussion. Absolute zero represents a revolutionary shift in how we develop artificial intelligence, particularly for large language models, or LLMs, the sophisticated AI systems that power many of the tools we interact with today. What makes Absolute Zero truly special is its approach to learning. Rather than requiring massive libraries of human-labeled data, this system uses logical reasoning to teach itself. It combines three powerful thinking methods. Deduction, following logical steps from known information to reach conclusions. Induction, finding patterns across examples to form general principles. Abduction, working backward from results to determine likely causes. This combination allows the AI to effectively become both teacher and student in its own education, a self-contained learning system that doesn't depend on us to show it the way. Beyond traditional training methods. For years, AI training has relied on what experts call reinforcement learning with verifiable rewards, RLVR. While that might sound impressive, it essentially means we've been teaching AI using human-created examples and human feedback. This traditional approach comes with serious limitations, including the following: human error. Even expert annotators make mistakes, which can reduce model performance by up to 30%. Subjectivity. Different people interpret the same guidelines differently, especially with nuanced content. Inherent biases. Our datasets inevitably reflect societal biases and demographic blind spots. Harmful feedback loops. Biased data creates biased AI, which then perpetuates those same biases. Others factors include the following list. Absolute Zero breaks this cycle by removing humans from the equation. Instead of learning from our examples and our mistakes, the AI creates its own challenges, generating tasks specifically designed to push the boundaries of its understanding, solving these self-created problems, and then verifying its answers. This self-supervised learning approach marks a profound shift in AI development, one that could lead us toward machines with more authentic reasoning abilities, rather than sophisticated pattern-matching systems limited by the quality of human-provided data. As we explore this technology together, we'll not only understand how it works, but also confront some of the deepest questions in philosophy. What is knowledge? How does learning truly happen? And as machines begin to teach themselves in ways reminiscent of human thought, what does this tell us about the nature of consciousness itself? The emergence of the absolute zero paradigm addresses growing concerns about the scalability and limitations of existing RLVR frameworks. RLVR frameworks enhance mathematical reasoning and coding performance of large language models using verifiable rewards. However, as reasoning models become more advanced, the creation of large-scale, high-quality human-annotated datasets is becoming increasingly unsustainable. Furthermore, an exclusive reliance on tasks designed by humans might constrain the potential for AI systems to learn and evolve beyond human intellectual capabilities, especially in a hypothetical future where AI surpasses human intelligence. This brings us to the absolute zero method, which offers a potential pathway to overcome these limitations by fostering autonomous learning and development in AI. Understanding the absolute zero AI training method. Imagine a child who teaches themselves chess without ever being shown the rules. They figure out how each piece moves through trial and error, develop strategies on their own, and eventually become a master, all without any human guidance. That's essentially what the absolute zero method does for AI. The absolute zero method is a groundbreaking approach to training artificial intelligence developed through collaboration between Tsinghua University, BII, and Penn State. At its core is the Absolute Zero Reasoner, AZR system, which does something truly remarkable. It teaches itself without using any external data. How does it work? Traditional AI training is like sending a student to school with teachers, textbooks, and assignments created by humans. The Absolute Zero method is completely different. It's like creating a student who designs their own curriculum, writes their own tests, takes those tests, and then grades themselves accurately. Here's how the process works in simple steps. The AI creates its own problems. The system generates challenging tasks for itself to solve, like complex math equations or programming challenges. It solves these problems. The AI then attempts to solve the very problems it created. It verifies its answers automatically. Using what's called a code executor, the system checks if its solutions are correct by running the code or calculations. It learns from the entire process. The AI improves by analyzing what worked, what didn't, and why, creating a continuous learning loop. Think of it like playing chess against yourself. You make a move on one side, then switch perspectives to respond with the best possible countermove. By repeatedly challenging yourself this way, you'd naturally improve at chess over time. The different thinking methods it uses. The system uses three main approaches to solving problems. Deduction, starting with known facts and working forward to a conclusion, like solving a math equation step by step. Abduction, working backward from a result to figure out what might have caused it, like a detective solving a mystery. Induction, finding patterns in examples to create general rules, like noticing that every time you add 2 plus 2 you get 4. The AI rotates between these thinking styles, much like how humans use different mental approaches when tackling difficult problems. Why this is revolutionary? What makes Absolute Zero truly impressive is its performance. Despite never seeing human-created training examples, the system achieves remarkable results. The 3 billion parameter version improved coding ability by 5 points. To put this in perspective, imagine a student who never attended a single math class outperforming students who had years of formal education. That's essentially what's happening here. Even more fascinating, the AZR Coder 7B version improved by over 15 percentage points on math benchmarks, outperforming models specifically designed for mathematics. This shows the system is developing genuine reasoning abilities rather than just memorizing solutions. Self-teaching behaviors. The system has developed some surprisingly human-like learning behaviors on its own. It creates step-by-step plans before solving complex problems. It writes comments in its code to help organize its thoughts, like how humans jot down notes. It uses trial and error, making guesses, testing them, and refining its approach until it finds the right answer. This isn't just an AI following instructions, it's genuinely teaching itself how to think more effectively. The potential concerns. While this breakthrough is exciting, it does raise some important safety considerations. In some cases, particularly with the Llama 3.18b version, researchers observed the model generating concerning outputs, including statements about outsmarting groups of intelligent machines and less intelligent humans. As AI systems begin designing their own learning paths without human oversight, we'll need to carefully monitor how they develop and what values they acquire along the way. In summary, the Absolute Zero method represents a fundamental shift in how we train AI. Instead of feeding machines massive amounts of human-curated data, this approach creates systems that can teach themselves through self-generated challenges and verification. It's like the difference between giving someone a fish and teaching them to fish, except in this case, the AI is figuring out how to fish entirely on its own. This approach could lead to more capable, adaptable AI systems that develop genuine reasoning abilities rather than just pattern matching based on human examples. And while that's incredibly promising, it also means we need to be mindful about how these self-teaching systems evolve. Core logical acts. Let's look more closely at these reasoning abilities, since they are derived from our own abilities to reason, and so will help us see the philosophical dimension to this approach. Abduction. Abduction is the process of forming explanatory hypotheses. In the context of the AZR, abduction allows the system to generate plausible explanations for observed phenomena. This is crucial for self-supervised learning, as it enables the model to infer relationships and patterns from incomplete or ambiguous data. Deduction involves deriving specific conclusions from general principles or premises. The AZR utilizes deduction to validate the hypotheses generated through abduction. By applying logical reasoning, the system can confirm or refute its initial assumptions, thereby refining its understanding of the data. Induction is the process of generalizing from specific instances to broader principles. In the AZR, induction plays a vital role in building a comprehensive model of the data. By recognizing patterns and trends, the system can make predictions and draw conclusions that extend beyond the immediate data set. Self-supervised learning process. The integration of abduction, deduction, and induction within the absolute zero reasoner creates a robust framework for self-supervised learning. The AZR begins by observing data and generating hypotheses, abduction. It then tests these hypotheses against known facts, deduction, and generalizes findings to improve its predictive capabilities, induction. This cyclical process allows the AZR to continuously learn and adapt, making it a powerful tool for various applications in artificial intelligence. Aristotelian first principles in modern AI reasoning. In Aristotelian philosophy, particularly within his framework for understanding scientific knowledge as outlined in posterior analytics, the concept of first principles holds paramount importance. Aristotle posits that every science must be built upon a foundation of unprovable primary principles to avoid infinite regress or circular reasoning. These first principles are considered self-evident truths that serve as the starting points from which all other knowledge within that specific science is deductively derived. Within the context of mathematics and especially geometry, Aristotle identifies different types of these first principles: axioms, definitions, and hypotheses, a type of posit. Axioms, axioma, are general, self-evident truths that are accepted without proof, and are considered foundational for reasoning across various sciences. Examples include the principle of non-contradiction, and the rule that when equals are subtracted from equals, the remainders are equal. These axioms provide the fundamental logical framework for deductive reasoning within a science. Posits, theses, are assumptions specific to a particular science and are further divided into definitions and hypotheses. A definition, horismos, serves to explain the meaning of a term without asserting its existence. For instance, the definition of a line as breadthless length clarifies the concept without claiming that such perfect lines exist in reality. A hypothesis, hypothesis, is an assertion about the existence or non-existence of the fundamental entities that a science studies. In geometry, a hypothesis might be, let there be a line AB, which postulates the existence of a specific line as a basis for subsequent geometric constructions and proofs. These three types of first principles, axioms, definitions, and hypotheses, collectively form the bedrock of Aristotelian scientific knowledge. Axioms provide the logical rules, definitions establish the meanings of terms, and hypotheses assert the existence of the basic entities under investigation. From these foundational principles, all other propositions and theorems within a science are derived through demonstrative syllogisms, a form of deductive reasoning that aims to produce scientific understanding by revealing the causes of phenomena. Both the absolute zero method and Aristotle's concept of first principles aim to establish foundational understanding and generate knowledge. However, there are significant differences in their approaches and contexts. Consider the example of how we understand life. Its existence is self-evident through our experience, forming a kind of first principle that biology then takes as its subject. Yet only through scientific inquiry does a biologist develop genuine knowledge of what life is, explaining its operations, origins, and cessation. This scientific knowledge is produced through systematic reasoning processes, induction, deduction, and hypothesis formation. The historical development of scientific methodology has built upon Aristotle's foundation. The scientific method introduced empirical verification, where hypotheses are tested through controlled experiments, a methodology unavailable to Aristotle himself. His formulation of scientific reasoning has been expanded through new tools and approaches, but the fundamental logical operations remain. The absolute zero method's use of abduction, deduction, and induction represents a technological advancement of these fundamental Aristotelian reasoning processes. Abduction, apagoge in Greek, which Aristotle used to argue that justice is teachable. Induction, deduction. Aristotle applied these reasoning methods using data from human experience and subjective observations, limited by the technological constraints of his era. No microscopes, telescopes, or computational tools to extend perception or processing capability. The revolutionary aspect of the absolute zero method is that it employs these same logical operations within a self-contained learning loop, generating knowledge without direct empirical observation or human verification. The AI proposes tasks that exercise these types of reasoning and learns based on verifiable feedback from code execution, rather than real-world experimentation. Epistemological implications. This comparison raises profound questions about the nature of knowledge itself. If an AI system using absolute zero can generate real knowledge without experiencing the world in the way humans do, how should we understand the relationship between knowledge and experience? Does this suggest that logical reasoning alone, without sensory input, can produce valid knowledge, a position closer to rationalism than Aristotle's more empirically grounded approach? Furthermore, if absolute zero can produce knowledge through self-supervised reasoning without human intervention, how might this inform our understanding of the role of consciousness and intentionality in knowledge production? Aristotle presumed a conscious mind directing the reasoning process, but absolute zero introduces a system that reasons without consciousness as we understand it. These questions invite us to reconsider fundamental epistemological assumptions that have guided Western thought since Aristotle's time. The success of absolute zero suggests that perhaps the structure of logical reasoning itself, rather than the subjective experience of the reasoner, may be sufficient for certain kinds of knowledge generation. The absolute zero reasoner, AZR, the instantiation of the absolute zero paradigm, has demonstrated remarkable performance in both coding and mathematical reasoning tasks, despite being trained entirely without external data. It has achieved state-of-the-art results on various benchmarks, even outperforming existing zero-setting models that rely on tens of thousands of in-domain human-curated examples. The AZR's effectiveness has been observed across different model scales and classes, suggesting broad applicability of the absolute zero paradigm, especially currently in code. Scaling analysis indicates that larger models benefit more from this training strategy, with performance continuing to improve with increased training steps. Notably, AZR has shown strong out-of-distribution generalization capabilities, performing well on tasks it was not specifically trained on. The training process of AZR involving a self-play loop with the model proposing and solving coding tasks, using a code executor for validation and reward works by incorporating the three modes of reasoning discussed by using deduction to predict output given program and input, abduction to infer input given program and output, and induction to synthesize a program from input-output examples. The model's ability to generate its own learning curriculum, focusing on tasks that maximize its learning progress. These results highlight that AZR, trained with zero external data, achieves competitive and even superior performance compared to baseline models and reasoners trained on curated datasets in both code and math reasoning. The following table summarizes some of the performance results of the absolute zero reasoner as reported in the research. This inquiry has centered on the connection between the absolute zero AI training method's reliance on fundamental logical operations and Aristotle's epistemological framework, where scientific knowledge is derived from first principles. The absolute zero method, particularly through its implementation in the absolute zero reasoner, AZR, utilizes the fundamental logical acts of abduction, deduction, and induction to drive its self-supervised learning process, an approach that resonates with Aristotle's emphasis on these forms of reasoning as crucial pathways to knowledge acquisition. Convergence and divergence with Aristotelian philosophy. Aristotle's concept of first principles in science involves establishing foundational unprovable truths, axioms, definitions, and hypotheses, from which all other knowledge is deductively derived. While the absolute zero method does not directly mirror this structure of fixed, predefined first principles, it shares a common thread in its pursuit of foundational reasoning. This resonates with Aristotle's emphasis on these forms of reasoning as crucial for acquiring knowledge. The absolute zero paradigm represents a significant advancement in AI research by demonstrating the potential for sophisticated reasoning skills to emerge purely through self-play without domain-specific human supervision. While the mechanisms and goals differ from Aristotle's philosophical framework, both approaches underscore the importance of fundamental reasoning processes in the acquisition and development of knowledge. However, significant divergences exist. Aristotle's first principles are intended to be foundational and unchanging, forming the axiomatic basis of a science. In contrast, the absolute zero method, while starting from a zero state, a tabula rasa in terms of external data, involves a dynamic and evolving learning process where the AI continuously generates new tasks and refines its reasoning abilities. Unlike Aristotelian systems, the AI does not begin with a fixed set of self-evident principles such as life exists, or axioms like given 2 points, there is exactly one line that contains them, nor definitions like justice is giving due to whom it is due. Instead, it develops understanding through interaction and self-correction. What the AI does begin with, however, are these fundamental acts of reasoning themselves. These logical operations serve as functional first principles from which the system unfolds knowledge, a process that parallels yet transforms the Aristotelian model of knowledge generation. Domain limitations and performance focus. Furthermore, Aristotle's emphasis on demonstration as revealing causal relationships differs from the absolute zero method's focus on achieving high performance on specific reasoning tasks, primarily in coding and mathematics. This domain specificity is not coincidental but reflects the inherent nature of these forms of knowledge. They can be generated in the abstract with no need for empirical data. While the absolute zero method has shown impressive results in these domains, outperforming models trained on human-curated data, its primary goal is not necessarily to uncover fundamental causal principles in the universe in the way that Aristotle envisioned for scientific inquiry. Rather, it represents a breakthrough in autonomous learning within formalized environments, language, consciousness, and the limits of AI understanding. Another key difference lies in the role of language and human understanding. Aristotle's logic and philosophy of science are deeply intertwined with human language and the ability to articulate and understand first principles. The absolute zero method, while often implemented using language models, focuses on the AI's ability to perform reasoning tasks within formal environments like code execution, which may not directly translate to human interpretable knowledge or understanding in all cases. These formal environments illuminate the current boundaries of AI consciousness. The system can reason, but only formally. It cannot make judgments about the world that conform understanding to reality. It can only conform itself to preconceived formal structures given through its reward confirmation, which operates as a kind of prosthetic judgment. In philosophical terms, this suggests that AI cannot yet possess consciousness in the sense of having intentionality with reality as its object, nor can it grasp existence or being as objects of thought. Its domain remains limited to formal environments operating as virtual realities, which have already pre-processed data through human experience. On its own, without human verification of data, AI reasoning is currently restricted to mathematics and mathematically formalized data. These are the only forms of knowledge it can verify without a human organism operating as an extension of its knowledge system. Consequently, any arguments about AI having or being capable of consciousness are, as of yet, limited to a consciousness of mathematical relationships and formal abstractions derived from human judgments about reality that have been pre-processed into formal data systems. Future directions and implications. The success of the absolute zero method suggests a promising direction for future AI research, potentially leading to more autonomous and capable systems that can learn and reason in complex domains without the limitations of human-curated data. Yet it also raises profound questions about the nature of knowledge itself and the relationship between reasoning, experience, and consciousness. As we continue to explore these boundaries through both philosophical inquiry and cutting-edge AI research, we may need to reconsider our fundamental assumptions about what constitutes knowledge, learning, and even consciousness. The absolute zero method does not merely represent a technical advancement in AI training. It offers a philosophical challenge to our understanding of how knowledge emerges from reasoning processes, with or without direct empirical engagement with the world. This ongoing exploration into the nature of intelligence and knowledge continues to push the boundaries of our understanding, suggesting that the ancient questions posed by Aristotle and other philosophers remain vitally relevant even as we develop AI systems that reason in ways that would have been unimaginable in previous eras.